The cross product, level 4. In this video, we're going to go over slightly more challenging examples that make use of both the geometric and component definition of the cross product. Let's go over the first example. Let u, v, w, and x be vectors in space. Which of the following expressions are meaningful? Which are meaningless? Explain your answer. Alright, for this problem, vector u, v, w, and x are all vectors in space. Recall that the dot product is defined for both vectors in r² and r³, while the cross product is defined for vectors in r³ only. Also, keep in mind that the dot product produces a scalar, and the cross product produces a vector. Let's use these facts and determine if the given expression is meaningful. Taking a look at the expression inside the parentheses, we see that we are taking the cross product between two vectors. This operation will produce a vector which will then be dotted with vector v, producing a scalar in the process. So this expression is meaningful. Let's take a look at the next expression. Here, the expression inside the parentheses is a dot product between two vectors, which reduces to a scalar. This scalar is then crossed with a vector. In this case, this expression is meaningless, because the cross product is defined only between two vectors. Let's take a look at the next expression. The operation inside the parentheses is a cross product between two vectors, which produces a vector. This vector is then crossed with another vector, which will produce yet another vector. So this expression is meaningful. Let's move along to the next example. The first expression in the parentheses is a dot product between two vectors, so this will reduce to a scalar. The expression in the second parentheses is also a dot product between two vectors, and it will also reduce to a scalar. In the end, we have a cross product between two scalars, which is not defined, so the entire expression is meaningless. Let's take a look at the next expression. Here, the expression in the first parentheses is a cross product between two vectors, so it will reduce to a vector. The expression in the second parentheses is also a cross product between two vectors, so it will also reduce to a vector. In the end, we have the dot product between two vectors, which reduces to a scalar. So this expression is meaningful. Alright, let's move along to a different type of problem. Find the cross product between vector A and vector B, and verify that it is orthogonal to both vector A and vector B. Notice that this problem is slightly different when compared to the examples from the previous video, since vector A and vector B both have functions in their components. This seems like a much harder problem, but the way you calculate the cross product is exactly the same. You just need to make sure that you apply the properties of exponents along the way. Let's start by setting up our determinant. Next, let's go ahead and find the minor for each component. Then, we go ahead and compute the determinant for each 2x2 square matrix, making sure we correctly use the properties of exponents when multiplying the natural exponential functions. Simplifying the expression for each component, we obtain the following vector for the cross product. Next, let's find the dot product of this vector with vector A and vector B. Simplifying the dot product, we obtain 0 for both vectors. Hence, vector A crossed with vector B is orthogonal to both vector A and vector B. Alright, let's try the next example. Find two unit vectors orthogonal to both vector A and vector B. Alright, the quickest way to find a vector that is orthogonal to both vector A and vector B is by taking the cross product between these two vectors. The result will create a third vector that can be easily normalized to obtain the required unit vector. We can then multiply the unit vector by -1 to obtain the second unit vector. So let's start by finding the cross product between vector A and vector B. Since we are given the components of each vector, let's go ahead and use the component definition of the cross product and set up our determinant. Once we have our determinant, we go ahead and find the minors of the matrix. Then we go ahead and compute each of the 2x2 determinants. Simplifying the expression, we obtain the following components for the cross product between vector A and vector B. Next, we go ahead and normalize this vector by dividing the vector by its magnitude. Computing the magnitude of this vector, we obtain the following. Then, it is just a matter of simplifying the components of each unit vector. The first vector will have the following components. And for the second vector, we simply multiply it by -1, obtaining the following unit vector. So these two unit vectors will be orthogonal to both vector A and vector B. Let's end the video with the final example. Find a vector v that is orthogonal to the plane that contains the points P, Q, and R. Here we're asked to find a vector that is orthogonal to the plane that contains 3 points. Recall that a plane is uniquely determined by 3 non-collinear points, points that are not all on a single line. In this problem, we're given the coordinates of 3 such points. In order to find a vector orthogonal to this plane, we need 2 vectors that are located on this plane, and compute the cross product with them. So our first task is to find 2 vectors that are located on this plane. We can easily do this by using the given points. Let's find the components of the vector formed by points P and Q first. So we subtract the coordinates of the points and simplify the expression, obtaining the following components for vector PQ. Next, let's find the components of vector PR. So we subtract the coordinates of the points with one another. Then, we simplify the expression, obtaining the following for the components of vector PR. Now that we have our 2 vectors, it is just a matter of taking the cross product between them. So we use the component definition of the cross product and set up our determinant. Then we find the minor for each component as follows. From here, we find the determinant of each 2x2 matrix. Lastly, we simplify each component, obtaining a vector with components equal to 8, 4, and 4. Note that any non-zero scalar multiple of this vector will also be orthogonal to the plane. This vector is going to be orthogonal to both vector PQ and vector PR, as well as a common plane between these 2 vectors. Finding a vector orthogonal to a plane is going to be extremely useful in this course, so it is important that you understand this example before you proceed. Alright, in our next video, we will switch gears and start covering and proving the algebraic properties of the cross product.